Good afternoon, everyone, and good night for those who are in Europe or in Finland, especially. It's a great pleasure for me to chair this session of the second edition of the International Virtual Seminar on Wood, Pulp and Biorefinery, organized by the Pulp and Paper Laboratory of the Federal University of Viçosa. My name is Cláudio Mudado Silva, and I am a professor at the Department of Forest Engineering, and I have been at the University of Viçosa, and I have been working at the Pulp and Paper lab for the last 21 years. First, I would like to thank the organizing committee, Professor Ana Márcia Carvalho, Felipe Pedersoli, Bruna Rodrigues, Priscila Moreira, Júlia Figueiredo, Marcela Coura, and Professor Yara Demuner. This is the first edition of this seminar was very successful, and I'm sure this second edition will be as successful as the first one. I would like to thank the university, and special thanks to the speakers who kindly accepted our invitation to deliver their lecture for us this afternoon or this evening. So welcome, everyone. In this session, we will have two speakers, both very qualified experts in their fields of work, of research. Dr. Tainise Vergara Loureson. She will talk to us about lignin fractionation. And the second speaker will be Dr. Alexis Metais. He will present about ozone bleaching status, challenges, and opportunities. So we will have these two presentations this afternoon, this evening. Each speaker will have approximately 1 hour to present, to deliver their talk. And after each talk, we will have around 30 minutes for questions and answers and discussion from the audience. So I'd like to thank you, the audience, as well. I'm sure that it will be a pleasure time you will have here and learn many things to our speakers. So I'm very happy to introduce the first speaker. Dr. Loureson received her Master of Science degree in Material Science and Engineering from the Federal University of Pelotas here in Brazil. And she holds a PhD in Forest Engineering from the Federal University of Paraná, also here in Brazil. But she has worked abroad as a researcher at the University of Basque Country in Spain in 2013, at Embrapa Florestas in Brazil during 2014 to 18, and at VTT from Finland in 2017. Since 2018, she holds a postdoctoral researcher position at Aalto University in Finland, at the Department of Bioproducts and Biosystems. Dr. Loureson has been devoted to researches in biomass conversion, lignin valorization, biorefinery processes, and wood science. So thank you very much again, Dr. Loureson, for your important participation in our seminar. So the floor is yours. Thank you.
Thank you very much, Professor Cláudio. It's a pleasure to be here. I'm very happy with this invitation. And today I'll be talking about lignin fractionation. My name is Tainise Vergara Lourençon, and I'm Brazilian, so I'm quite happy to be talking at this seminar, especially with this massive presence of Brazilians here. I will just talk a little bit more. Just a minute. Okay, about my background. It has been mentioned, most of it. So I have my education basically from Brazil. I am a wood industrial engineer, and my master's is in material science, and I have a PhD in forest engineering. Those are all universities in Brazil. And during my master, I spent some time in Spain, in the University of Basque Country. And then during my PhD, I had the opportunity to come actually to Finland, but I went to VTT, to the VTT Technical Research Center of Finland. During my PhD, I also had a collaboration, so it was between Ivswpb and Embrapa Florestas. So after I finished my PhD, I moved to Finland. And I'm now working, as it has been mentioned, in Aalto University in the Department of Bioproducts and Biosystems. I'm now at the research group called Wood Material Science and Technology. But before that, I was a bit more than 2 years working in the lignin chemistry group. So my history with lignins, well, it doesn't start here. It actually started during my PhD, basically, where I started going deeply on research in lignin. And with PhD and these years and until now, although I'm a beginner in my career, it goes there 7 years of research focusing on lignin. The outline of this presentation, so just to give you an idea what I'll be talking about. So I'll talk about lignin sources and lignin structure, isolation methods for lignin, why to fractionate lignin, what are the methods used to fractionate technical lignin and other lignins. Then I'll talk a little bit more about some fractionation methods I've worked with, which was salt-induced precipitation and sequential acid precipitation. Then I'll tell you a little bit more about these obtained fractions. And then I'll show you some applications in which we tested these fractions. Then, if time permits, I'll be talking about biorefinery lignins. And then we go to final considerations and then to questions. We have this global increased interest in natural resources. And this is due to the fact that fossil feedstocks it will be in the future will be limited and ending. And this is a really good opportunity, and this really encourages us to look for renewable materials. And this is really good in our fields because we have lignocellosic biomass. And in plant biomass, we have the three main building blocks: lignin, hemicellulose, and cellulose, which are really interesting polymers. And there is a lot to do with these renewable materials. And here I bring actually something for us to think, that usually when we talk or when we read papers about these lignocellosic biomasses, We have this thing that we need to replace petroleum-based materials, but until we really get no fossil feedstock, it will be a long way. So to be competitive and to maybe to accelerate the to bring these renewable materials to the commercialization, we could try to focus on trying to finding new features for these materials, not really replace. It's really hard to compete with synthetic polymers. So we can think and focus on trying to find new features of each of these polymers and build new bio products. And of course, I will be talking about the potential of lignin here. And lignin has a wide range of applications. It spans from chemicals, polymers, adhesives, composites, carbon fibers, packaging, and so on. We have, probably most of you have read something about lignin, and the first thing we see is that this is the most abundant aromatic polymer that we find on Earth, or is the second most abundant natural polymer after cellulose. And this is true. Lignin is a really important component in plant biomass. In wood, it brings stiffness and it brings the resistance to wood. So, for instance, the water cells don't collapse, among other characteristics, important characteristics for the plant. We also know that this polymer is amorphous and complex. Lignin has these three, the laser here, has these three main phenylpropane units that they are the main building blocks of lignin, and depending on the degree of methoxy groups here, the methoxylation degree, they differentiate from each other. So we have parahydroxyphenyl here, guaiacil, and syringil. And lignin is complicated because it depending on the plant that it comes, it will present different amounts of these units and the whole polymer. For instance, if we are dealing with hardwoods, we will have higher amounts of syringil and then guaiacil and trace of parahydroxyphenyl. While if we are dealing with softwoods, we basically have guaiacil units there. Or if we work with grasses, annual plants, or agricultural residues, then we have higher amounts of H units, but some amounts of G and S units as well. And how we can isolate lignin? Actually, in lab scale, there are many ways to isolate lignin, but I'll tell you a little bit about the process that we have industrially. And this process, they are side streams. They are not really focusing on lignin, not until now. So lignin there is a byproduct. And we have here in the left examples of lignin resulting from pulping process. Those are also called technical lignins. We have here this 2-sulfite and Kraft process in which we have the sulfur content in the process. And sulfite was quite used until 100 years ago, and it's still decreasing its use. Basically, we now have Kraft as the main process. In Brazil, for instance, we only have Kraft process. And sulfite lignin has the big difference from others because it has this sulfite units in the aliphatic chain. So it makes lignin soluble in water, and it has been quite applied in dispersants and concrete and among others. Then we have these organosolvent soda processes that they are more used for annual plants. They use milder conditions. They are not really severe enough to separate the fibers from lignin and hemicellulose. So that's why they are used more for annual plants. Then we have other processes that are basically they focus mainly on the production of sugars for the conversion into biofuels. And here we can cite hydrothermal treatment, HTT, which use water only and temperature, but temperature we have in all of them. Then we have acid hydrolysis, which we have also water, but with addition of acid. We have supercritical water hydrolysis, enzymatic hydrolysis, steam explosion, and from all this process, lignin, as I said, is a byproduct. So why to fractionate lignin? So I guess at this point, if you are following my thoughts, you have seen that lignin is quite complicated, and it has a variety that comes from the source. And so summing up with the isolation method, we end up with the soup of things. So it's quite heterogeneous, and it will, if we, for instance, take this spent liquor, the black liquor from a craft process, we will have quite polydispersed lignin there with varying in terms of chemical structure, consequently in reactivity, in hydrophobicity, and other properties. So the idea with fractionation is that we can narrow these variations, and we can then we end up with these specific fractions with known characteristics. It's believed that and it makes sense that if we know exactly what we have there in this fraction, it should be easier to destinate such fraction for a certain application. And then we would have a more efficient utilization of this fraction of this lignin. So I selected here some of the fractionation processes that are mainly used or that we can find in literature. So we have filtration, solvent fractionation, and acidification. In filtration, we have the use of membranes. It's called also this ultrafiltration. Then lignin is separated by its molecular size, so we can have different molecular sizes. There is something more recently using hydrogel for filtration of lignins, but not for technical lignins. Then solvent fractionation has been quite used. So mostly for technical lignins, these organic solvents, methanol, ethanol, acetone, dioxane, THF. And then lignin is solubilized in, it can be sequential. It can be solubilized in these solvents. Then there is, it's also more recently that we have ionic liquids, but this was not for craft or sulfite process. It has been tested in this soda lignin, and some attempts in this for greener solvents as GVL. and glycerol, but those were used in this enzymatic hydrolyzed lignin. Then we have acidification, in which we have mostly the use of sulfuric acid and hydrochloric acid to precipitate lignin. This is quite used, and I put here some pros and cons of each fractionation process. So from filtration, we get this advantage that we can have in each fraction narrow molecular weight. And for instance, in low molecular weight, we have high OH groups. As cons in this filtration is that usually we still have carbohydrates present in the fraction. We might have some clogging problems, and we have expensive instrumentation. In solvent fractionation, we can have as advantage the unique chemical characteristic of each fraction. For instance, in terms of phenolic content, or one fraction will have carbohydrates while the other won't have any, and so on. And as a disadvantage, well, before we solubilize this lignin in any of the solvents, we would have to precipitate this from black liquor, for instance, if coming from craft process. So it's one extra step, and then we spend in this in the solvent. Then in acidification, the advantage is that this is a simple process. It's cost effective, and that we can directly fractionate this from black liquor. There is one disadvantage that at least it has been observed that high yielded fractions usually had lower purity. So we still had some ashes and some carbohydrates there, but in the end, it might be that this is not a disadvantage, and you'll tell about this a little bit more. So now I'll tell you about some fractionations that I have worked with. And first, we worked with this fractionation by Saltinduced precipitation. And why we fractionated with salts? Because because our idea was to fractionate with acid. And as I just mentioned, usually when we use acid to fractionate lignin, we used either hydrochloric acid or sulfuric acid. And when we use these acids, it's released an counter ion, sodium. So when protonating, the lignin is protonating. So we have the formation then of sodium chloride when we used hydrochloric acid, and the formation of sodium sulfate when we used sulfuric acid. So we wanted to understand what was the effects of chloride and sulfate anions upon the precipitation of craft hardwood and softwood lignin. So the idea is that we have the lignin polymer, and we have the water molecules, and we add these ions, and we want to understand the ability of this ion in reducing the water activity solvation in the lignin polymer. So how these different anions work. In our process, we started with an isolated lignin, and we solubilized in sodium hydroxide, and then we add salt, both sodium chloride and sodium sulfate. We then ultrasonicate to make sure the mixture was happening and the reaction was happening, and then we let it rest, and we centrifuge. then we, after centrifugation, we got so here in the salt addition, we add different concentrations of salt. You'll see in the next graphic. So when adding the salts, each concentration precipitated lignin. So we recovered this precipitated lignin, and we alkalinized again in sodium hydroxide to measure the absorbance in UV. And what we could observe from this research is that, let me show you. So this graph here is the normalized absorbance in the y-axis, and x-axis we have concentration of salt in mole per liter. So what we can see first, if we compare both salts to precipitate lignin, so in the left we have the sodium sulfate, is that for sodium sulfate, we needed basically half of the concentration that we needed in sodium chloride to precipitate both hardwood and softwood lignins. So sodium sulfate was much more effective to precipitate lignin. Here, I put the ionic force just in the salt saturation point for you to have an idea that, in fact, for sodium sulfate here, we have at a lower concentration a much higher ionic force than in sodium chloride, and this is due to the anions that we have here. What else? When we compare hardwood and softwood, in both cases, in both salts, we can see that softwood precipitated with different concentrates, precipitated more easily than hardwood. And why softwood precipitated was easier precipitated? We can associate that to the molecular mass of softwood. So if we compare here our two lignins, we see that the average molecular mass of softwood is basically 3 times higher than for hardwood. And during lignin precipitation, we basically have 2 main factors involved, which is pKa, and molecular weight. As we don't have here any change in pH, we can associate this to the molecular weight. So the bigger fragments that we have in softwood, when the salt was added, destabilized the solution, and softwood was easily fragmented and precipitate. The bigger fragments of softwood was then precipitating first. Another support information from this work is from FTIR. We can see the higher degraded lignin that we have for hardwood. We can see here at these vibrations, so you see the intensity of these peaks here for CO, CC, CO, methyl, methylene groups. So this hardwood lignin is in fact more degraded. It has lower molecular mass, and due to the syringyl groups, so due to this methoxy group in the C5 position, this lignin is easily attacked by the alkaline during the craft process, and therefore more degrade. So from this work, then what we can conclude in summary is that, so here green is our anion chloride, orange is our anion sulfate. We can see that if we compare, at least I try to illustrate here, that when we have chloride, we still have water molecules solvating the lignin, while for sulfate anion, it has a more efficient solvation effect. It brings all the water to solvate the ion than the polymer. So with the sulfate, we would have a higher recovery, while for chloride, we have a higher solubility. So main conclusions, the sulfate anion was more effective than chloride to precipitate lignin. A pronounced precipitation for softwood lignin was associated to its higher molecular mass. And controlled cosmotrope salts. These cosmotrope salts are water structure makers. So they arrange a strong hydration complex away from the hydrophobic surface of craft-lignin. So these salts addition, they promote a fractionation of both hardwood and softwood craft-lignins. So after this salt-induced precipitation, we worked with acid precipitation, and then we chose to work with hydrochloric acid. As we saw, the hydrochloric acid didn't, the salt that we will be released in the solution won't be affecting the precipitation. So we believed we would control better the precipitation with acid. We have used, again, craft black liquor, both from hardwood and softwood. So we started with black liquor at pH more or less 13. Then we add HCl until we reach pH 9. At this pH, we had precipitation of lignin already, and we recovered through centrifugation, and this supernatant comes back to the process. This was done under stirring. And we add more acid to the supernatant until pH 7. So it was a sequential fractionation. We have more precipitation of lignin at this pH 7. Then supernatant comes back to the process. We add more acid until pH 5. And then we recover through centrifugation this fraction at pH 5. Supernatant comes back to the process. We add more acid and we precipitate the rest of the lignin. So we fractionated these 4 fractions. All the fractions were washed with acidified water to get rid of the further impurities. Then they were dried at milder temperatures. And now I will tell a little bit more the characteristics of this fraction. So I will start showing you the main differences between fractions that we can see, and also between hardwood and softwood. So in the left, we have the molecular mass distribution of hardwood lignin fractions. And here in the x-axis, we have retention time. So the bigger molecules, they will appear in the lower retention time with higher intensity. And we can see here, both from these peaks and also from the average molecular masses, that we had sequential fractionation of the molecular mass. So in fraction 9, we had the higher molecular mass, then it was decreasing as the pH was decreasing. It was nicely fractionated, this for hardwood. In the case of softwood, we didn't have success in terms of separating by molecular mass. So you can see here it's much higher. So it was bigger fragments. It was much more difficult to fractionate this lignin. We had still higher, a bit higher molecular average molecular mass for fraction 9, but then they were similar here, and they didn't really present a trend. So the next results that I'll be showing you, they will be more regarding the hardwood lignin fractions. We do have more characteristics of both hardwood and softwoods. You can check in the paper that I mentioned at the bottom of the previous slide. But here, to simplify, and as later I will be showing about hardwood, I'll tell you more already about hardwood fractions. In terms of yield of this acid fractionation, we have basically almost half of the lignin is being fractionated at pH 9, and then we have considerable amounts of lignin at pH 7, and then we have really low yields at the lowest pH 5 and 3. And I'm not showing here the softwood, but the yields were similar for softwood. But continuing with the hardwood fractions. So here we have chemical composition of these fractions, the hardwood fractions. We have here, this is acid-insoluble lignin, acid-soluble lignin, ash, and carbohydrates. We have here the fractions, and to simplify, we can look these darker colors here are, if we sum, they are total lignin in the lignin fraction. So they are the purity of how pure these fractions are. And we can see, if we trace a line here, that fractions 5 and 3, they presented the highest amount of lignin in the lignin fractions. And what we had in the fractions as well was amounts of ash that comes from the sodium, from the craft process. And in terms of carbohydrates here in the top, we have similar amount for all of them, which is around 2% only. In terms of hydroxyl groups, which we can measure quite with accuracy with phosphorus NMR. Here we have for the hardwood fractions, and we have more results. I try to put the simplified table here, but we can see if we look at aliphatic OH groups, we see that they decrease with the decreasing of pH. This is slightly difference, but it decreases. What happens with the phenolic OH is the opposite. It increases with the decreasing of pH in the fractionation. So as total OH, we have higher OH groups in those fractions 5 and 3, which also present a higher purity of lignin. So now I'll show you some applications or some potential applications that we tried for this hardwood craft lignin. First, these antioxidant and tumoral activities of lignin fractions. So all these applications I'll show now, they will be with these hardwood fractions. So for antioxidant capacity, we have used this common DPPH assay in which we have this DPPH that is reduced in the presence of an antioxidant, and then we have a color change that can be measured in UV. Sorry, Professor Claudio, I think I can hear you in the background. Maybe if you mute, I don't know if it's disturbing others. Okay, thank you. So these are the results for antioxidant capacity. I placed here this as DPPH reduction, but there are other ways that we can present antioxidant capacity. Here, I think it's easier to see. We had 100% DPPH and how much we were able to reduce of this. It means that if we reduced more antioxidant was this lignin. So we tested 3 concentrations of lignins for all fractions. From the lowest concentration, we can already see higher antioxidant capacity of fractions 5 and 3. but it greatly increased when we increased concentration, and always following this pattern of having fractions 5 and 3 as the main or as the most antioxidant lignins. And this is quite nice number for a reduction if we 8%. If we compare with other lignins or non-fractionated lignins, it was much higher. So we could compare this with other lignins in literature. We tried to correlate these fractions 5 and 3, the composition of these fractions, to understand what was the chemically there that was making them more antioxidant. And we did this with GCMS. We do have higher alpha CH2 content, also methox substitution there, and those are known as the as antioxidant, as they have antioxidant capacity. But we also had this higher alpha COO and CCC, which would reduce the antioxidant capacity. So we believe that those work simultaneously. Then we associated the higher antioxidant capacity of fractions 5 and 3 to the highest purity of these fractions, and also to the lower molecular weight of these fractions. What else we find in this study is we evaluated these lignins as antitumoral to see its antitumoral activity. It was a collaboration during my PhD. It was also in UFPR. So we tested the lignin activities in 2 gliomas, these 2 tumors. And one was a responsive tumor, another one was resistant. And this responsive and resistance is regarding to this chemotherapy already used. So if they were, these are known as responsive and resistant to the chemotherapy that we already have in use. And as a reference, it has been used non-tumoral cell, which is this human dermal fibroblast. It's skin cells, as good cells. And the methodology here used is actually simple. So this MTT protocol is used, and these salts in MTT, if we have active cells, so if the tumor cells are viable, they will form this formazan, which has this violet color, and it can be measured in UV. So as a result from this antitumor activity, we have here for responsive glioma, we have here is control with all viable cells, 100%. And then we have each fraction in different concentrations. And for all the fractions, we had a decrease in tumor viability, especially at higher concentrations. So the lignins, especially 975 or with some exception here of fraction 3, then they presented really interesting results in activating or reducing the viability of these tumoral cells. But this was for this responsive one. Then for the resistant tumor, we also have, especially at higher concentrations of fractions, and also for the same 9, 7, and fraction 3, mostly fraction 7 and 5, I would say. They had a statistical difference. They presented some decrease in the tumoral cell viability. So this was the responsive and resistance resistant to glioma is what I said. It's regarding to how they react for the standard chemotherapy. We could see the higher concentration presenting a better effect against the tumors. We still don't understand, or we still don't know, we still have to understand the mechanisms how lignin acts as antitumoral. And we did not see correlations of our most antioxidant fractions with the antitumoral activities. Another interesting finding from this research is that when we tried the lignins, this is really important, when we tried with the good cells, with the non-tumor cells, our cells with the addition of all lignins, except here in the higher concentration, which was less than 5% reduction, basically kept all good cells viable. This was quite interesting. It doesn't really help if we find antitumoral activity in lignins, but if they destroy good cells as well, right? So main conclusions from this work. So we had black liquor, fractionation, we tested bioactivities, and what we saw is that when we had lower pH fractionated fractions, we had lower yield, lower molecular weight, and we had higher antioxidant capacity. I did not show here, but we also got interesting results from for antibacterial activities of lignins, and antitumoral activities we saw for all fractions, but mostly in those fractions from pH, intermediate pH. So a little bit to conclude about the antitumoral, all lignins presented bioactivity. We didn't see correlation with antioxidant capacity. We see nearly no growth inhibition on non-tumor cells by lignin. And it's not yet possible to correlate lignin specific structure with the bioactivities. And this is also another application that we tested with our hardwood fractions, which is phenylformaldehyde resins. Actually, the use of lignin in phenylformaldehyde resins is what we have closer to the market nowadays. In Finland, if I'm not mistaken, we already have the replacement of phenol in this formaldehyde resins with lignin. So I'm not sure if it's in pilot scale or if it's already in the industry scale. So these thermosetting polymers, they are used in many applications in automotive, computing, aerospace, buildings, but also and mostly in the manufacture of engineered wood products as LVL, plywood, OSB, particle board. And so the lignin phenylformaldehyde resins, or phenylformaldehyde resins, this is phenol. Phenol has 3 reactive sites here in its aromatic ring, which reacts with formaldehyde for further condensation. So the idea is that we have similarities. It's not the same, but we have similarities in lignin building blocks. So in the lignin building blocks, in H, we have these 2 reactive sites. In G, we have 1 and none in S. And those reactive sites would react with formaldehyde. And as you see here, we have non-reactive site theoretically in hardwood lignin from S. We would have from G. So what we could find in literature or in the studies is that hardwood wouldn't be suitable for replace phenol in these resins because the number of reactive sites will be much, much lower than softwood, for instance, because softwood basically has only guaiacil and some age. So in this work, we showed how it worked with hardwood lignins. And the synthesis of the resin, it takes place in two main steps. First, there is hydroxymethylation. So what we did, we had the lignin molecule, we add the formaldehyde, and so this hydroxymethylation takes place. And for this first step, we used only lignin before we add phenol. I say that we still add phenol because our resins we did with 50% replacement. So 50% by weight of phenol we replaced with lignin. And then the second step is when the condensation happens and we add, so then the hydroxymethylated lignin, phenol, and increased temperature is an alkaline medium. We had this methylene bridge and also ether linkage and the formed polymer. Another thing that we did in this work that was different from others is that we did a parallel or a previous evaluation only using this hydroxymethylation. And why we did that? Because so how people who do the recipe to know how much of formaldehyde to add, they usually can see the OH groups from phosphorus NMR, so they can see in the aromatics how much of reactive sites they would have, and they would add formaldehyde according to that. But we did this hydroxymethylation preliminary, so we could see actually how much of formaldehyde was being consumed by lignin. And I'll show here these results. So we have here the lignin fractions, and we have softwood. This was another craft softwood just to compare. And those results come from phosphorus NMR. So the calculation is that we consider G times 1 and H times 2 for all of them. And you can see that, in fact, softwood has much higher reactive sites compared to hardwoods. However, when we take the results from this hydroxymethylation only, we can see the actual consumption of formaldehyde. And you see with the solid bars that for hardwood lignins, we had basically the same actual consumption than it was theoretically calculated. And it didn't happen for softwood. So softwood, although it has or present more reactive sites, it has much higher molecular weight, probably steric effect. So there are many other things taking place and playing different roles during the resin synthesis. So how was it when we evaluated bonding strength? So this is AB's test. We have here, this is really a nice test because we just need this thin veneer. We apply time, press time and temperature as much as we want. And we can evaluate the bonding strength. Okay, I was trying to pause the video. So here are the results for bonding strength. We can see here our 4 hardwood lignin fractions. This was the softwood, and this is a PF resin that was synthesized without lignin. Just to compare, we can see that it's still only PF is still quite has higher bonding strength, but we have quite suitable bonding strength when we add all lignins. Here I selected this temperature and this press time, but we tried many times and other temperatures. And what we can see, although here we see a better performance of our fraction 5, which was actually statistically the same as 7, but we can see that hardwood lignin, the bonding strength was not worse than softwood, was even better in some cases. So there was no disadvantage of these hardwood lignins. Then, as main conclusions from this work, one is that the consumption of formaldehyde, so we showed that theoretical is really not reflecting the actual consumption, especially for the softwood lignins. So we can say that the number of reactive sites is not the only important factor in the synthesis of LPF resins. And here, actually, and this is common, I guess, in our research, that we raise more questions. So for this kind of applications, do we really need to fractionate the lignins? Because although we didn't have much better bonding strength for those fractions with really low yield. So maybe we don't really all these fractions. And we have a practical outcome from this work, that is hardwood kraft lignins have no disadvantage compared to softwood in LPF application. So final considerations for this kraft lignins part. So what is really good about kraft lignin is that we have ready-to-use resource. We have tons of lignin from the craft industries. Other considerations from this fractionation, I would say that maybe we don't really need all these fractions. Maybe if we had fewer fractions, would be more feasible to apply industrially in the industry. And actually, we have a challenge from this technical lignins, because we have the lignin as it is. It's a byproduct. Deal with it, and then we have to find solutions. So we have to find applications, but maybe if we know the application, then we can try to engineer to really find the characteristics of the lignin that we need. And another thing is that we could use some suggestions for these fractions. We could use, for instance, this low purity lignins, as in pH 9, that we still had ash there. You saw that there was basically no disadvantage in the LPF resin. So maybe it could be applied for LPF resins, which is there's no high market price compared to other high value add applications, but we need larger volumes, and we have good yields in these fractions. And then maybe other fractions with higher purity we can apply for antioxidant or other applications with high market prices. Now I think I still have a few minutes. So I have talked about fractionations, considering technical lignins, but this biorefinery lignin is a sort of fractionation, but it's a different point of view. This work was developed here in Aalto when I was in the lignin chemistry group. So we applied hydrothermal treatment, but in our case, we didn't focus on the production of sugars. We focused on the production of lignin. Lignin was our mainstream. So we applied this HTT, hydrothermal treatment. We used birch wood and water only in the reactor. We applied different temperatures, different times, different water to solid ratios. And this has a consequent severity of the process, which we measured as a P factor. So as high as if the higher P factor, we have higher severity of the process. So after this HTT, we have two resulting products. We have the hydrolysate and the HTT solid. So in hydrolysate, we have hemicelluloses that has, we can then use this as side stream for sugars and fuels. But our focus was here. So we took these HTT solids and we applied a quite simple and affordable process at room temperature. So we add this aqueous acetone to the HTT solids, and we extracted lignin directly from these HTT solids after the HTT. So here we have the acetone extracted lignin and the resulting extracted solids, which is a cellulose-rich fraction, which also has nice potential applications. And we could recover the acetone here and use lignin, but we went further, trying adding value to this lignin. So we did like a controlled drying of this lignin to produce lignin micro nanoparticles. So here we could use directly the lignin soluble in acetone as precursor here, and we collect the micro nanoparticles here. But from this work, as I won't have much time, I will tell you the main findings. So my idea here is to show that from one side, from the technical lignins, when we have the craft black liquor, for instance, we try to fractionate and narrow the characteristics. And here we try to go the other way around. So we are engineering lignin from the beginning. And the other fractions from the process, cellulose, hemicellulose are the side streams, but they are still have quite good market price. So we engineered, because you can see here, this is the molecular masses of our fractions. So P factor was increasing, so severity was increasing. In this case, we had set 1 liquid to solid ratio, and it was 1 temperature. So timing was changing, was increasing, and the average molecular mass was increasing to a certain point. Then lignin, we believe it starts to condensate, and it's really hard to solubilize in acetone. So we had different lignins here. We could correlate the different molecular masses. So here we had higher severe process or higher molecular rates, and we can correlate with contact angle. So we see that the contact angle increased when we had higher molecular range. And we don't have hydrophobic lignin, we didn't reach the 9th the angle, but we have a less hydrophilic lignin. And it was nice to be able to compare this contact angle of lignins, because what we see in literature is comparing softwood with hardwood, but one from craft process, another one from organosolv process, and they all have different characteristics, and it's really not reasonable to compare. Another thing from this process that can be mentioned here, so this is from carbon NMR. I just put here these beta-4 methox groups and oxygenated aliphatic, because these linkages show how degraded lignins are. And we have here this craft organosolv just to compare. And this in gray is use the liquid to solid 8 in a mild process, and a liquid to solid 4 is green in a mild process as well. But this liquid to solid 8 was the mildest process that we had, and we can see here that we preserved better the structure of lignin. And as lower we have these values, as in craft, for instance, we have really degraded, for instance, beta-4. This really shows that we can engineer different lignins just playing with the HTT treatments. So in summary from this work, we have a simple, green, and affordable process for biomass conversion. And we have applications, we have potential applications for all process streams, being lignin the main one. I didn't show here, and I also don't have time to show all the characteristics of the micro nanoparticles, but you can, and please take a look at our paper here in the bottom. But we were able to get quite high yields of lignin when we extracted from these HTT solids. It got up to 90% of the original lignin we were able to extract at room temperature. And it was quite pure lignin without carbohydrates. So also we could have molecular weight and chemical structure of lignins tailored by playing with this hydrothermal treatment conditions. As a take-home message, I would say I have said so many conclusions of so many different works here, but in general, and from what I've learned so far, is that maybe if we understand that we cannot find, or we cannot say that, or find one lignin and say that this lignin is best for everything, or really, there is no way we can say that. So maybe if we find, if we engineer different lignins, we will then find suitable applications for these lignins. It's really complex, so we really have to take this into consideration for have nice and competitive products from lignin and then apply. I'm very thankful to all universities. I have whole universities, so the universities in which I have in this studies, and institutes, and both in Brazil, in Finland, and also the fundings I had at the moment of the works. And I would like to thank you all for listening. And if you have any questions, I will be happy to answer.
Thank you very much, Tainise. Can you hear me?
Yes.
Okay, I'm sorry. First of all, sorry about the disturbance of the noise. I've been doing this call through my cell phone because my computer in the tests previously did not work. I got a little bit confused here, but sorry, I hope I did not disturb.
No, it's fine. It was just this background noise. I wasn't sure, but I think it was from your mic.
That's right, yeah. Well, thank you very much for your excellent presentation, very rich. And we do have, some questions here already. Maybe some more will come, but I will start with the first question from Luan Cavalheiro. Luan asks, are there any studies to find a less polluting chemical to extract lignin from the cell wall? Which chemicals are being used?
Yes, I guess I mentioned something. Let me try to find out. First, thank you for the question. Just let me go here to this slide. So what we see is some researches that are trying to use greener solvents, these ionic liquids, or these GVL or glycerol, they have been cited as less harmful solvents, but I didn't see these solvents to extract or to fractionate. For instance, kraft lignin. It's really hard to solubilize lignin. So this is one big challenge. But I think we already have some efforts towards that. Or for instance, this last work that I showed. So this is not yet a technical lignin. This was a different approach, a biorefinery approach that we suggested. So we used water and for cooking the wood, basically water temperature. And then we used only aqueous acetone to extract lignin. And acetone is quite mild compared to other solvents. And we didn't publish, but we could try ethanol, and this can be recovered and have a closed cycle in the industry.
Okay. The second question, Caio Zandonadi, he asks, industrially, in the lignoboost process, there is a maturation step to precipitate lignin. Was this also necessary in your lab experiments?
Thank you for your question, Caio. A maturation process, well, I'm not really used to this wording, but no, we didn't use any previous precipitation. In this lignoboost, they used this CO2 to precipitate lignin, and the pH at this point is 9. And then they can further acidify this lignin to recover it all, and the pH goes directly to pH 2, and they can recover lignin, and also that the liquor can come to the initial state of the kraft process. So if it was applied to the kraft industry, they could still use the CO2 to get to the pH 9, maybe to spend less acid. This could be applied, but no, in the process that we used, we didn't have any maturation step. It was directly the acidification with hydrochloric acid.
Okay. Jessica Gomes, she asks, are there other parameters apart from the pH that can affect the acid lignin precipitation, such as temperature, for example?
If I'm not mistaken, there was one research in which they evaluated the temperature, but now I don't recall if it was affecting. But the two main factors that are taking place during the acidification is really the pH, the protonation of the lignin, and the molecular weight. This has been quite cited in literature as being the two main factors. But it might be that playing with temperature, we increase lignin solubility at some pH. Maybe we would have a better separation of lignin. But I don't recall from this one paper that now came to my mind if they found any really results showing that.
Okay. Alessandro Miguel Ferreira de Souza asks, is there some information related to the pH and dissolved lignins in the hydrolyzed liquor?
Can you repeat the question, please?
Okay. is there any information related to the pH and the dissolved lignins in the hydrolyzed liquor?
In the hydrolyzed liquor, I'm not sure if I understood this question, but for sure the pH is completely affecting the black liquor, the liquor where the lignin is, because when we add the acid protonates this lignin, and then lignin starts to agglomerate and precipitate. So depending on the pH, as I showed with the different pH, it will be, we would have the, different recover at different pH. So pH for sure destabilize the liquor.
Okay. Julia Cristo asks, during your presentation, you said that in the acid precipitation, lower yield fractions have higher purity. In your opinion, could this be a challenge for scaling up the process?
Yeah, I guess I believe that the challenge here is that, is it really needed to, for instance, I had this lower yields at two fractions at pH 5 and pH 3. And let me show you again this here. So yeah, pH 5 and 3, we precipitated really low yields, and yes, these were where we had the most pure fractions. So I believe if this was applied or scaled up, this process was quite simple approach to fractionate, just continuing adding acid and recovering lignin. But of course, if we go to lower pH, further steps would be needed. But the big question here would be if we would have nice applications to, so that would explain that we have to go all the way to get this low yielded fraction. So maybe if we have really high value add applications in which we need only low amounts of lignin, and then the market prices are really good, I'm sure that the industries wouldn't mind of spending more in the process and reaching this low pH and getting these low yielded lignins, because they would have nice application or good return, good revenue. So the big question would be if if we would have nice high value applications to explain really the application of these low yielded fractions. But would be doable in industry, I believe so.
Okay. There's another question here from Mustafa Rohilf. We want to utilize lignin for 3D printing based on the source. Which one do you suggest with better antioxidant properties?
Okay, thank you for the question. Okay, as I tried to show in the beginning, it's really hard to compare lignins. It varies from different sources and different isolation methods. So it's like comparing orange and apples at some point. So what could I say? Well, maybe what I could see here is that lignin has a nice antioxidant capacity, and we got this good antioxidant capacity in these fractions 5 and 3, for instance, but fractions 7 and 9 also had antioxidant capacity. So maybe craft lignin itself, as just precipitating it from black liquor, would be enough to apply for 3D printing. But maybe the first challenge to 3D print with lignin would be the mixture with the polymer, the homogenization, and all these factors. But it's it's really hard to say. I don't know if it's possible to say between. It depends on what you want. Between, let's say, organosolv lignin or this sigma lignin, which is a sulfonated lignin, or craft lignin, which one will have the highest antioxidant capacity? Maybe you can compare them. Maybe you can use these technical lignins, or one craft and one organosolv lignin, just to have this good approach in which you are using a technical lignin, which is already available, so you have a nice justification. But maybe I don't have numbers here, but maybe lignins not from pulping process, but from sugar biorefineries, they would have a better performance in 3D, or they would have a better antioxidant capacity. It's really, again, I come back to the beginning, it's really hard to say between one lignin or another in terms of process of isolation. Maybe you would have to consider other factors, as I said, the homogenization with polymer, among other things. Sorry that I can not really help specifically saying this lignin is the best one for that.
Okay, no, it's a variety of parameters to consider. Yes.
Yes.
We still have one question here from Alexandre Oliveira. He asks you to clarify, did you took black liquor sample and add sulfuric acid to achieve pH 9 and beyond? And if this understanding is correct, could you comment about the H2S emission?
No, we didn't add sulfuric acid. We know that sulfuric acid is the mainly acid used in industry. So, for instance, in this lignoboost process, quite used also in Brazil. They precipitate lignin, so first to this pH 9 with CO2, and then they used in the end, when recovering lignin, either for trying applications or to burn to generate energy, they use sulfuric acid. But in our case, we have used only hydrochloric acid directly. So we directly add hydrochloric acid, HCl, in the black liquor we got from the company. So I cannot tell about the H2S. But I'm sure this is another, there are other researches and views on that.
Okay. Well, I think that was our last question from the audience that they sent during the chat. Well, thank you very much, Tanise, for your great presentation, for your research. We understand the great potential of lignin and to be used as material for the industry or other applications, such as those anti-tumoral activity in the medical science area. Very, very nice. Interesting. Yes, very, very nice. So again, congratulations for your presentation and for your work. We wish you all the success in Finland and in Brazil too, whenever you come.
Yes. Yeah, thank you. Thank you very much. Thank you again for the invitation, for the organizers, and for all the questions. If you have any other questions or if you want to contact me, so this is my email, my name, surname, and auto.com, I would say, .p. Yeah, thank you very much, everyone. Thank you, Professor Claudio.
Thank you, and have a nice summer, or spring and summer now.
Yes,
Finland,
yes.
Right?
Yeah. Looking forward to that. Thank you very much.
Thank you. Well, I think now we continue with our seminar, the second international virtual seminar on wood, pulp, and biorefinery. And it's a pleasure for me to introduce the next speaker this afternoon, and who will be speaking about pulp bleaching. Dr. Alexis Matos will talk about ozone bleaching, status, challenges, and opportunities. First of all, I would like to thank Dr. Alexis for contributing to our seminar. And a very short introduction. Dr. Alexis Matos is a global pulp and paper key account manager at Xylem, the world's leading supplier of ozone systems. He has served in this position since September 2015, after having joined Xylem in January 2008. And he worked then as a sales engineer and then worked as a business development manager. Alexis holds a master in pulp and paper science from the Grenoble University in France and a master business administration from the Lyon University. Well, again, thank you very much, Alexis, for your presentation. I'm sure that we will learn the challenges and the opportunities and what's going on with this so important chemical for bleaching, ozone. The floor is yours.
Hello, everyone. Thank you very much, Professor Moudadou, for the kind introduction. Just a comment, I'm not a doctor, so I'm only engineer. That being said, un prazer para mim de apresentar, um prazer apresentar o branqueamento com ozônio e os seus desafios e as suas oportunidades. E primeiro queria agradecer aos organizadores pelo convite e principalmente a Júlia Cristo pela comunicação e agora ao professor Mudadu pela apresentação. But my Portuguese is quite limited, so I will now come back to English. Can you confirm that you see my screen on the presentation?
Yes, we can see it.
Okay, thank you very much. So there will be three main parts in that presentation. What is ozone bleaching today? What are the challenges or the hurdles that ozone bleaching is facing? And what could be some development opportunities? But first of all, I will start by saying a few words on xylem and on ozone, and on its production. And on that picture here, you see Suzano Jacarei, which is today the biggest pulp mill using ozone. There are two fiber lines there, and both of them use ozone bleaching. So what's xylem? Xylem is a US-based company. It's a world-leading supplier in water technologies. And we have a revenue of $5 billion US, more than 16,000 employees, and we are present all over the globe. We are producing and selling different products, and all of them are related to water. Our main brand is called Flight. It's from Sweden, and we are producing pumps. And these pumps can be used for water treatment, wastewater treatment, on very specific applications. We have a big department with Census, where we are selling a lot of flow meters, sensors to control the water flows and the water quality. And among these different brands, one of them is called Vedeco. And at Vedeco, we produce ozone and UV systems. Ozone generators are today produced in Germany, in Herford. And now I will say a few words about ozone for you to have some insights about that chemical that maybe you heard about, but have no clear understanding about what is that. So in the airs that we breathe, there are 80% nitrogen and 20% oxygen, more precisely dioxygen. And ozone is formed by 3 oxygen atoms. It's a very strong oxidizer. It is actually the strongest oxidizer that is available in the pulp and paper industry. And it's unstable, because once it's produced, it reverts back into oxygen. So it cannot be stored, and it should be produced at site and used right after production. It's a gas, it's very smelly, and we start smelling the ozone at a concentration of 0.01 ppm, which is much lower than the dangerous concentration. For example, it's allowed to work 8 hours with an ozone concentration of 0.1 ppm. It means that in case there will be some ozone leaks, it's easy to stop ozone production and to avoid any safety issue. So we have air from the outside, from the atmosphere, and from the air, some oxygen is produced, and we have pure oxygen. And in the pulp and paper industry, we use that pure oxygen to produce ozone. And we need for that electricity. With electricity, we create an electrical field that breaks some oxygen molecules, and we'll have some formation of O3, ozone. Not pure ozone, in fact. We are able to produce ozone at a concentration of, let's say, up to 15% by weight, the rest being oxygen. In the pulp and paper industry, we use typically an ozone concentration of 12-13% by weight, meaning that the rest is pure oxygen. And we need as well cooling water. Cooling water because, in fact, close to 90% of the electrical input is transferred to heat. So it's not a reaction which is extremely efficient, and we need to remove that heat from the ozone generation system. But these are the three items that are needed to produce ozone. Electricity, which is produced outside from the recovery boiler, so it's green electricity from biomass. Oxygen, also produced outside from air, which is free, and green electricity, and cooling water, which is reverted without any impact on its quality. Here is how it looks like an ozone generator, or let's say it's a corpus. So it's like a heat exchanger, and on the left, we'll have oxygen flowing in the small tubes that you see, and we'll put some electrodes in these tubes. And in these pipes, some oxygen will convert into ozone. And on the right, you see that there is space between the pipes, and we have cooling water circulating between each pipe. So here at the bottom on the right, you see somebody putting electrodes in the ozone generator vessel. All the vessel is made of stainless steel and glass, so there is no moving part. It's not like a chemical reaction that you can see in the lab or in a chemical plant. In fact, we do not see anything when we look at an ozone generation unit in operation. There is gas getting in, gas getting out, but the color is the same of the gas. And there is no specific noise, no smell. It's only gas, cooling water, and electricity management. Here is how it looks like a system. So on the right, you see the ozone generation unit with all the valves, the sensors. And on the left, you have a power supply unit. So each ozone generator is fed by 1 or 2 power supply units. And typically in the pulp and paper industry, we deliver ozone plants in a container where we have the ozone generator on the right and all the electrical part on the left. That container, which is 17 meters long, 3 meters and a half width, 3 meters and a half high, can produce up to 5 tons pure ozone per day. So 5 tons pure ozone per day, considering that ozone is at 12% concentration in oxygen. It's possible to put that container on the ground or to put it on some strip fundaments to have all the utilities coming from the bottom. So the footprint of an ozone plant is extremely small. And one advantage of that approach is that it's modular. So we can put 2-3 containers in a row, depending on the needed ozone capacity. It's also possible with the same footprint to put two containers, one on the top of a first one, with ozone generators at the bottom, and all the electrical units at the top. And with that same footprint, it's possible to produce 10 tons ozone per day. Advantages of that design is that it's fully tested in Germany, where it's mounted before it's shipped. There is no specific new building to build at the pulp mill site. There is no noise issue. And it's a plug-and-play system. You just need to put electricity, cooling water, oxygen, and you produce ozone. So it's a pure on-site technology because oxygen is also produced at site. And ozone does not need any transport or storage of chemical precursors. It's not like, for example, chlorine dioxide, where sodium chlorate needs to be imported, transported, stored, with all the logistics and storage issues and safety issues. To produce 1 kilogram ozone at 12% by weight, we need 8.3 kilogram oxygen. It means that at the inlet of the generator, we have 8.3 kilogram oxygen, and at the outlet of the generator, we have 1 kilogram ozone and 7.3 kilogram oxygen. And the conversion of oxygen to ozone requires 10 kilowatts, more or less, per kilogram ozone. So these are the two main figures that you need to consider when doing some cost calculations. As an indication, you can as well consider 2 cubic meters of cooling water per kilogram ozone. And now I start addressing the case of ozone bleaching. So when we look at the chemistry, there are two families of chemicals that were used, have been used, or will be used in pulp bleaching. We have the chlorine family with chlorine, hypochlorite, and chlorine dioxide, and we have the oxygen one with ozone, oxygen, and hydrogen peroxide. And in fact, each of these chemicals react with the lignin in different ways. And today, chlorine dioxide reacts, which is the chemical which is mainly used in pulp bleaching, reacts with the free phenolic groups on some CC double bonds. But it does not react with all the phenolic groups on CC double bonds as elemental chlorine was doing in the past, but it's now forbidden, and as ozone is doing today. So when we look at that table, it's quite easy to understand that a bleach plant combining ozone, chlorine dioxide, oxygen, and hydrogen peroxide can remove more lignin, so more chromophores and more chromogens than a standard ECF bleach plant. So by using ozone, it's possible to reach higher brightness and higher brightness stability. And that assumption, which is based on simple chemistry, is of course confirmed in the lab and at full scale. The first pulp mill that operated ozone bleaching is Lenzing in Austria. They started in 92. And the growth was quite fast in the 90s because it is the time when chlorine bleaching was banned in Europe, Brazil, the US. And some pulp mills made the choice of ozone over chlorine dioxide with the idea to have a TCF bleaching without any chlorinated chemical. At that time, some also used ozone together with chlorine dioxide. But let's say in the 90s, it was quite new. And how to use ozone was not very clear with chlorine dioxide, only with TCF. In comparison, the first applications for pulp bleaching with chlorine dioxide appeared in the 1940s. So it was 50 years before ozone. The second step of the ozone bleaching growth was in the 2000s with Japan banning chlorine bleaching. And then from 2008, there is a small drop related to mainly pulp mill closures in Europe due to the crisis. And for now, the last 5 years, the growth started again, mainly supported by China, because China is a country where environmental regulations are the strictest for new pulp mills. And also with the demand for viscose pulp, where ozone has a clear advantage, technical advantage over chlorine dioxide. On that list, you can see all the pulp mills in operation with ozone bleaching. So we are close to 30 pulp mills. Some were delivered by Xylem, they are in blue. Some by others, they are in white. It does not matter. Here we speak about ozone bleaching. And what we can notice is that most of these pulp mills are producing kraft pulp. That's clear that sulfide pulp is a very small minority today. Most of these pulp mills are bleaching hardwood pulp. Only a few of them are producing softwood, 5, 6. And that's due to the fact that most of the pulp mills actually produce hardwood pulp, and the share of softwood pulp globally is quite small. And in average, the capacity of these bleach plants is between 1,000 and 2,000. However, we see, for example, the number 26, Chenming Shuguang, where the capacity is 3,600 tons per day. And that's today the biggest fiber line with ozone. Their bleaching sequence is ZD-EOPD, and they use ozone at medium consistency. For your information, in Brazil, so we have the number 6, Suzano, where ozone was started in 97 on line B, and then it was installed on the green field line C in 2002. It was also installed on the number 4, Bahia to the Sateri in 96, and soon, and also in the international paper Luis Antonio, number 5, and soon Lenzing Duratex will start a pulp mill with ozone in Brazil. So when we look at that list, we see that Nippon Paper, OG Paper, and Lenzing operate ozone in 3 mills each. And considering the seriousness of these companies, it's quite a good sign about the reliability of ozone bleaching. Some other companies like Sappi, Chenming, and Paper install it in 2 mills. And some other companies, UPM, Mondi and Suzano, installed it once in 1 pulp mill, but then expanded capacity also with ozone by adding new ozone capacity. So the choice of ozone has been confirmed quite a few times by different pulp companies and pulp mills. When we look again to the table, we see that in the last lines, we find most of the time the same bleaching sequence, which is ZD, EOPD. While in the first years, there were quite a few different bleaching sequences. It means that finding the appropriate way to include ozone in the bleaching took time, optimization was needed, errors were made, but somehow, after 10, 15 years, there was a clear consensus about putting ozone at the beginning of the bleaching and not in the middle. And if possible, with only 2 washers for hardwood. There are two ways to mix ozone with the pulp. One is delivered by Valmet. It's called the Z-Track. The pulp first goes to a specific press, where it's pressed to a consistency of 38-42%. It's fluffed. And then it goes to a screw reactor, where it reacts with ozone during 1-2 minutes. And at the outlet of the screw reactor, the pulp gets diluted and is submitted to a short extraction stage that takes 5 to 10 minutes. That process allows in 5 to 10 minutes to replace D0 EOP that take much longer, at least 2 hours. So it's a very, very fast bleaching compared to standard DCF. A typical bleach plant with the Z-Track is that one, so Z, washing, D, washing, and P. And with that bleaching sequence, it's possible to bleach hardwood and softwood for paper grades and also for market pulp. The second process is mainly supplied by Andritz. It's done at medium consistency. So it's in the same consistency that is followed all over the bleach plant. So after a pump, ozone is injected in 2 mixers or 1 mixer depending on the ozone dose. And here the difference with the high consistency process is that ozone needs to be compressed. So while the high consistency process is operated at atmospheric pressure, more or less, here ozone is compressed to 10 to 12 bar gauge and injected in the mixers. And then the ozone reaction takes place in seconds, 2 or 3 seconds. The pulp then flows to a reactor on a blow tube. But even if we call it a reactor, in fact, these 2 small towers are mainly used to stabilize the flow and to remove all the gas from the pulp before going to the pump to avoid any cavitation. The gas which is taken out from the pulp can be reused in other applications, can be used in oxygen acidification, in the EOP stage for white liquor oxidation, or in the effluent treatment plant. A typical bleaching sequence with ozone at medium consistency is ZD, EOPD, where there is no washing between ozone and chlorine dioxide. It's a very compact solution. And it is the bleaching sequence that has been preferred in the last years when we look at the different references. A big advantage of ozone, and it is actually the reason why ozone is known, why it was used in the 90s, is that with ozone, it's possible to get a better effluent quality, mainly because we can recirculate a part of the bleaching filtrates to the post-oxygen washer. So we can recover more COD to the boiler and discharge less COD. So when we compare D-hot EOPDD with ZDP, we see that it's possible to reduce bleach plant effluent by 4 cubic meters, COD by 40%. AOX, of course, are decreased a lot if you use less chlorine dioxide. And color is also reduced. And some pulp mills reported extremely good results, like, for example, Saltinduced in Portugal, producing eucalyptus pulp, with only 5 cubic meters per ton of bleaching effluent, and only 10 to 14 kilograms COD per ton. So that pulp mills produces TCF BKP. Australian paper reported with an ozone bleaching stage at medium consistency, 12 cubic meters from the bleach plant, 122 kilograms COD. In short, it's possible to reduce COD by 40% with an ozone bleaching stage at high consistency, or 20% with a ZD combination. Here you can see some bleaching chemicals consumption from pulp mills on hardwood. So a typical hardwood ECF bleaching requires 14, 15 kilogram chlorine dioxide. And if using ozone, we can use 5 kilogram ozone and 3 to 7 kilograms chlorine dioxide, depending on the wood species, on the bleaching sequence. Again, you see that the ZD EOPD here leads to the best results. It's also possible to produce softwood pulp with ozone bleaching with more or less 5 kilogram chlorine dioxide, 5 kilogram ozone, and 10 kilogram hydrogen peroxide. You see mill B producing TCF pulp with ozone, 6 kilogram ozone, 20 kilogram hydrogen peroxide. And when you compare mill C, where it's more or less 5, 6 for each chemical, you see that it's very competitive against a state-of-the-art pulp mill with ECF bleaching, where for softwood, somehow 17, 18 kilogram chlorine dioxide are needed. So that was about the environment, about the chemical consumptions. And then I'll address here with a few slides the pulp quality. some people from the 90s still have in mind and then communicated that ozone would impact the pulp quality. In fact, it's like everything. It's only a question of dosage. So if too much ozone is used, then yes, the pulp quality will be destroyed. But today, with all the automation, it's possible to adjust very precisely the ozone demand, and the ozone generator will adjust its production automatically to the need. So it will not produce more ozone than needed. And with that, we see, for example, on mixed European hardwood, on that slide presented at that time by Mezzo, that ZEO DND and DZEO DND led to higher tier than standard DCF bleaching. So today there is somehow a consensus about the fact that ozone bleaching does not lower pulp quality on hardwood pulp. There are some people still have some concerns, more or less justified on softwood pulp, but I'll come back to that point later. A big push for ozone is the use of dissolving pulp, the production of dissolving pulp. And for example, Peter and Lima published in 1998 a paper reporting their operations in Brazil with ozone. And they said that the extractive content is extremely low, and they did not see any scaling or pitch problem. And for dissolving pulp, ozone is used for mainly viscosity control. So once, like for dissolving pulp, once we have removed almost all the lignin, 1 kappa is around 2, ozone will react almost directly with the pulp, with the cellulose, and it will somehow reduce the viscosity to the targeted viscosity. And because the ozone generator can produce the needed amount of ozone in seconds and adjust its production, we can really add the needed ozone dose according to the online measurements. In the case of paper grades, where we still have kappa 10, 8, 6, ozone does not have the same impact on the pulp quality. It can somehow deteriorate the viscosity, but as we saw in the earlier slide, tear and tensile can be higher. So here are some results from Brazil with viscose pulp. You see that only 3 kilogram ozone and 8 kilogram peroxide are needed to produce an excellent quality dissolving pulp. 3 kilogram ozone, 8 kilogram peroxide. It's extremely little. And the bleaching sequence is AZP. So it's a very short bleaching sequence as well. And for dissolving pulp, probably a shorter bleaching sequence can be considered, like ZQP, for a pulp mill aiming to produce only dissolving pulp. In the case of swing mills aiming to produce dissolving grades and paper grades, then it can be the standard ECF bleaching, DOPDP, or ZD-EOPD. Here you see on these results from the lab that the ZECF bleaching sequence, so ozone and chlorine dioxide, led to very impressive results with especially a brightness that was kind of uncontrolled up to 94. So I said a few words about the cleanliness of the pulp in dissolving pulp. And actually, it's not only the case of dissolving pulp, but as well of paper grades. There are quite numerous publications reporting less extractives in ozone-bleached pulp than in standard ECF pulp. And that means that the pulp mill can spend less money in pitch control chemicals. So here on that slide, you see some results from a full-scale installation with a slide from hundreds. And at the bottom, it's from, again, another pulp mill, where the general manager stated that low bleaching cost and minimum pitch problems were the main drivers for using ozone bleaching. And it's in a pulp mill producing market pulp for paper grades. Another benefit of ozone bleaching is that it somehow acts as a chemical refiner. So ozone bleached pulp requires slightly less refining energy to reach the same chopper. So it can be important for some paper mills. Now we'll address the case of economics. So when we look at the chemistry, 1 kilogram ozone replaces 1.7 kilogram pure chlorine dioxide. That's chemistry. In practice, of course, that value can depend on a few parameters, but it is on that value that I will base the short calculation that follows. So let's consider that in a pulp mill, 1 kilowatt costs 4 cents, 1 kilogram oxygen costs 8 cents, 1 kilogram chlorine dioxide costs 1.2 euros. Let's recall that production of 1 kilogram ozone requires 10 kilowatt and 8.3 kilogram oxygen. Therefore, 1 kilogram ozone costs €1.06. Typically, a pulp mill uses 4 to 6 kilograms ozone. So if considering that every kilogram ozone replaces 1.7 kilogram chlorine dioxide, the use of ozone allows for saving €5 on chlorine dioxide per ton of pulp. But on the top of that, savings on pitch control chemicals, lower steam cost, because in fact, every time we inject chlorine dioxide in the pulp, we inject a lot of 99% of chilled water that needs to be compensated with steam. And of course, if using ozone, we can lower the effluent treatment cost by rejecting less COD, less color, less AOX. So in conclusions, ozone bleaching brings several economic, ecological, and quality bonuses: lower bleaching costs, similar or better strength properties, higher brightness stability, lower pitch content, precise viscosity control in the case of dissolving pulp, lower content of OX in the pulp and AOX in the effluent, lower COD on color discharge. But there are still a few challenges that are somehow still breaking down the growth of ozone bleaching, even though if every year, as we saw, the capacity of ozone bleached pulp is growing. Some experts still believe that ozone means TCF, and that when using chlorine dioxide, they should not use ozone. But in fact, if we come back to the reference list, we see that most of the pulp mills using ozone also use chlorine dioxide. So ozone is mainly used in ZECF bleaching, while TCF is limited mainly to dissolving pulp production and to a small amount of pulp mill producing from time to time TCF pulp for paper grades. But for paper grades, it's mainly ZECF with, for example, ZD-EOPD. So in the 90s, it's true that there were some pulp quality problems on hardwood and softwood. On hardwood, it's been cleared. On softwood, it's still a concern, mainly because, in fact, there have been very little softwood projects over the last 20 years. It's only now in Scandinavia that we see again new softwood pulp mills. But the ideas of the 90s were kept in mind. In fact, here I'm showing some results where ozone is tried in the middle of the ECF bleaching sequence with 1 kilogram. At the beginning, with 3 kilogram ozone in a ZD combination, and also at the beginning with a high ozone charge of 6 kilogram ozone per ton of pulp. We see that the brightness with ozone is higher, and that in these lab results, ozone replaced more than 2 kilogram chlorine dioxide per kilogram ozone. But it's in the lab. What matters are the following results. So here you see the PC number that shows the brightness stability. And we see in blue the standard ECF curve, and in red at the bottom, the bleaching sequence with 6 kilogram ozone. We notice that the more ozone was used, higher is the brightness stability. It's not a surprise, but it's good to keep it in mind, especially for market pulp that is shipped to China, and the trip can take 1-2 months. So that brightness stability issue may be of some importance, especially for market pulp producers. Then when we look at the tensile, we see that all the bleaching sequence have somehow the same tensile. There is no difference with or without ozone. And then there is the case of the tear. And here that's very interesting. We see that at the bottom there is a red curve where 6 kilogram ozone was used. And it's with that ozone dose that we have the lowest tear. So yes, it's true that if using too much ozone, we are reducing the tear and we are reducing the pulp quality. But somehow the highest curve, so the best tear, was obtained with ZD, where only 3 kilogram ozone was used. And in purple, with 1 kilogram ozone, the tear was still higher than with standard ECF. So it's possible on softwood, as we saw the case for hardwood, to get better pulp quality with ZECF than with standard ECF. It's just a question of dose. And typically, if we want to get a higher quality, the ozone dose should be limited to 3, 4, maximum 5 kilogram ozone per ton of pulp. Then that's more related to your specific case in Brazil, where ozone on hot acid hydrolysis have been seen as competing techniques. So if we look at some bleach plants producing eucalyptus pulp, standard DCF bleaching sequence, DEOPDD, needs 14 kilogram chlorine dioxide and 3 kilogram peroxide. Marivale in Australia, also on eucalyptus, needed 6 kilogram chlorine dioxide, 3 kilogram peroxide, 5 kilogram ozone. Okay, of course, it's always tricky to compare pulp mills from different countries, different cooking processes, but it's an indication. And when we look at these results, we see that 1 kilogram ozone somehow is the same as 1.7 kilogram chlorine dioxide. But for eucalyptus pulp, for now 15 years, it is standard to have a hot acid stage at the beginning, either with DHOT or with AD, depending on the fiber line supplier. So I added in the table the bleaching sequence from Veracel, DHOT, EOPD, P. We see that, of course, it's much more competitive than the standard DCF with 8 kilogram ozone, chlorine dioxide, and 3 kilogram peroxide. So it's an extremely low consumption of bleaching chemicals. And when we compare it to the standard DCF bleaching sequence, of course, the cost of bleaching chemicals is slightly higher with ozone because ozone removes the xenuronic acids, while in the DHOT bleaching sequence, xenuronic acids are removed by acid, which is kind of free. But still, the standard DCF bleaching sequence is competitive because we have one bleaching step less. So it means less capex for the tower and for the washer, less OPEX for the electrical energy and for the steam. And somehow, ZECF is kind of competitive for eucalyptus, even against DHOT or AD bleaching sequences. But somehow, pulp mills in Brazil and in Indonesia, in other countries, have been doing the choice of DHOT. But in fact, when we look at at the literature, there are quite many articles on that, but we see, for example, the article from Ragnar and Daloff that compared standard DCF and standard ZECF with DHOT and ozone after hot acid hydrolysis. And when we compare a DHOT bleaching sequence with an AZ bleaching sequence, we see that the amount of chemicals is reduced accordingly. And again, we are finding that replacement ratio of 1.7 when we are comparing carrots with carrots. So when we are comparing the impact of bleaching chemicals against the impact of bleaching chemicals, and not against bleaching chemicals plus the pH of acid hydrolysis. So in fact, A and Z are not competing, but can be combined if a washer is installed. So we can have a bleaching sequence, for example, A, Z, Z without any washing, P, with only 2 washers, and that could be a competitive bleaching sequence for eucalyptus pulp. ozone will be expansive. So here is a paper we published at the last ABTCP. We considered 1,200 tons per day pulp mill. So it's of course more related to Europe than Brazil, but it gives some indication. And we looked at the capex of the different elements, including the cost of the ozone plant and the cost of the chlorine dioxide plant. And in fact, at the end, it was a surprise for us. We saw that a bleaching sequence, a bleach plant and a chemical production at site is less costly when ozone is used than in the case of standard ECF. When we look at the OPEX, it's not a surprise. We already said a few words about that. With ozone, it's possible to save money on dispersant, on the steam, and on chlorine dioxide, of course. And in that study, we found that it was 6 euros per ton of pulp that were saved by using ozone. But in fact, about the economics, there are two concerns that are questioning the fact of using ozone. The first concern is that in Brazil, for example, pulp mills are used not to invest in chemical production. And there are some chemical suppliers installing at site chemical islands where the pulp mill can purchase chlorine dioxide over the fence. And so far, ozone suppliers have been operating with another business model where they sell the ozone plant and do not sell the ozone as a chemical. So, in fact, as a result, it makes that capex with ozone can be slightly higher because most of the time, chlorine dioxide production is outsourced. And one challenge for ozone is to align with that business model and probably to offer ozone over the fence to avoid for the pulp mills. So it's at the end, it's more expensive for the pulp mill. It's better and cheaper to purchase and to operate. But of course, when we invest, we always try to reduce the capex as much as possible. So it makes sense. Another drawback of ozone, when we look at the economics, is that ozone is produced at site from electricity produced at site in the recovery boiler. And modern pulp mills make a lot of money by selling pulp, but they also make very significant amount of money by selling green electricity to the national network. So by producing ozone, they reduce their chemical cost, so they are saving money, but they also reduce their electricity sales, so they are gaining less money. And it is sometimes a balance between these two aspects. And on that topic, AFRI recently published a case study on dissolving pulp, where they looked at the electricity sales benefits, and they retracted from that the bleaching costs. And in that study, they found out that even by selling less electricity because of ozone production site, OPEX were still better if using ozone than if using standard ECF, which is the case one in that graph. Case one is standard ECF, case two is ZECF, case two is TCF, and case three is ZECF. So that's a very interesting new publication showing that even if considering the sale of electricity, it's economical to bleach with ozone. A few opportunities to finish. So ozone bleaching allows to optimize bleaching chemicals cost and better recirculating the alkaline filtrates to the post-oxygen washer. Thanks to that, it limits the need to invest and operate tertiary effluent treatment that are very costly, or big chloride removal systems to protect the recovery boiler from chlorides. Sometimes people look only at the different departments separately, the cooking, the recausticizing, the bleaching, the effluent treatment plant. But in fact, the use of ozone impacts effluent treatment and impacts the recoast as well. And by using ozone, we can save on these two departments. So another opportunity for the future is the use of TCF pulp with A, Z again, and P. And in some cases, probably one Z step can be removed. And that bleaching sequence allows to have the lowest emissions possible at a very competitive cost. For example, for TCF, we can speak about 5 kilogram ozone and 10 kilogram peroxide max on eucalyptus. And that bleaching sequence, if applied, could be related to the concept of a green chemical island, where oxygen is produced at site from green electricity and air available for free. From that oxygen and green electricity, ozone is produced. And from green electricity, hydrogen is produced by water electrolysis to produce hydrogen peroxide. And at the end, it means that it's possible to have all the bleaching chemicals produced at site from green electricity produced by biomass, from air and water, without any delivery or storage of hazardous chemicals. I see I have 2 minutes. I will very quickly go to other ozone applications. So ozone is used for bleaching. It is the main application for pulp and paper. But it can be used for NOx elimination at the outlet of the recovery boiler. And that's a growing topic with more and more requests. So far, it's quite limited at full scale, but there are some strong interest. Ozone can be used to treat intake water to remove chromogens before they will yellow the paper. Ozone can be used to detoxify some specific products, specific chemicals that are applied on the paper. And it can be applied in the effluent treatment plant for discoloration or for hard COD removal. In the pulp mill and in paper mills, ozone can as well be applied for cooling water treatment in place of chlorine-based chemicals. So, obrigado pela atenção, and I would be very happy to reply to your question, give some more details, and discuss any concern that we may have. Thank you very much. And you're welcome as well to contact me anytime at alexis.metais@xylem.com.
Thank you very much, Alexis, for your nice presentation. Yes, we do have some questions here for you. So I will start with Daniel Lima. He asks, here in Brazil, pulp mills don't use ozone on large scales. Do you think this is due to high cost implementation of the ozone plant?
Actually, here in Brazil, there are 3 pulp mills using ozone. It is Bahia from Sateri, producing dissolving pulp with ozone. They have 2 lines, one ZTCF and one ECF without ozone. That's and then there is international paper Luis Antonio. So Bahia started in 96, international paper Luis Antonio in 97. And there is also Suzano Jacarei that started in 97 and built a new fiber line with ozone in 2002. So there are some full-scale installations in Brazil with ozone, on quite big ones, because Fibria Jacarei is a big mill. But it's true that ozone has not been successful over the last almost 20 years. So it's not much a question of pulp quality. I think it is related to 2 points. First, it's related to the growth of the dehot AD stage, so where we combine a low pH, high temperature, and long retention time to remove hexenuronic acids. That has proved successful and very economical for eucalyptus pulp. And the fact that ozone is also very reactive on hexenuronic acids. So many people saw ozone as competing against hot acid hydrolysis. Personally, I think, and it's one of the challenges I addressed, I think that it's possible to combine these 2 techniques to remove hexenuronic acid first with a hot acid stage, then wash the pulp, and then go with ozone. And with such an approach, then a small shot of chlorine dioxide can be applied, of course, but then it should be possible to get very good eucalyptus pulp with TCF. But so I think one of the first issues was in the 2005, 2010, the taking over of the dehot AD solution, which is a very good process. And which somehow won over ozone at that time, but probably it can be combined in the future. And the second aspect is the fact that chemical suppliers of chlorine dioxide offer chemical island with all the chemicals needed to the pulp mill without any investment. They sell chlorine dioxide over the fence, while in fact, ozone suppliers are more small companies. They do water business, they don't do chemical sales. So we are not in the same market mind that standard chemical suppliers. And when a pulp mill is interested, they've been requested to purchase an ozone system while they get a chlorine dioxide system for free. So the business approach is different. And I think that it has a significant impact on the market situation in Brazil. Probably if ozone suppliers or new partners would invest in ozone systems in place of the pulp mills and offer the sale of ozone as a chemical, would help to get new installations. Then a last comment on that question. Still, in 2022, a new pulp mill starts with ozone in Brazil. It is Lansing Duratex, and they will produce 500,000 tons per year of dissolving pulp. So ozone has been facing difficulties here, but still there are some wins from time to time.
Okay, thank you. Well, just I have other questions here, but I just would like to ask one question of mine. Is there any marketing pressure for low OX pulp? Because I remember in the 90s was a big competition on TCF and ECF, and was really based especially on environmental aspects of the bleaching sequence or the bleaching plant. It seems that the ECF sequences, they became more popular, not only in Brazil, but worldwide. Because they kind of proved that in terms of toxicity, the effluents would not change if you have a ECF bleaching sequence or a TCF bleaching sequence. But anyways, my question is there any environmental pressure from the market in order to lower the organochlorine on the pulp?
Yes, actually, no, there is no clear pressure from the market on that. Today, ECF bleaching aligns with the local regulations on the market standards. So there is no clear benefit for pulp mills to have less OX in the pulp or less AOX in the effluent. Okay. That's clear. But still, I'd like to remind that most of the pulp mills using ozone use ozone and chlorine dioxide together. So ozone does not exclude chlorine dioxide, and chlorine dioxide does not exclude ozone. Ozone is mainly used in the ECF bleaching, and then ozone has two benefits compared to standard ECF. It is the economics, okay? But still there is an environmental benefit for the pulp mill. With ozone, it's possible to discharge less COD and less effluent. And in the case of some local regulation, ozone still bring a valuable environmental benefit.
Okay, yeah, well, there's another question here that comes later. We can discuss a little bit more about this point of the water usage and effluent quality. But Priscila Moreira asked, that's the second question here we received, the ozone stage can influence on the stability of the pulp brightness?
Yes. So when ozone is used, brightness stability is always better than in the case of standard ECF. And actually, the reason for that is quite simple. Ozone reacts very strongly on hexenuronic acids. And hexenuronic acids are the main responsible for brightness reversion. So because the ECF removes more hexenuronic acids than standard ECF, the ECF allows for a better brightness stability.
Okay. Marcus Mladenovic asks, do you think that in the future there will be players, for example, industrial gases producers, that will sell ozone over the fence?
I think it can be part of the solution to avoid capex on the pulp mill side. And if one or some oxygen suppliers would offer ozone over the fence, I strongly think it can change the situation, for example, in Brazil. Because it is part of their business model. Today, when oxygen is needed in every pulp mill, at least for oxygen nullification, and oxygen suppliers sell oxygen per kilogram or per ton. So they are used to invest and then to sell a chemical. So if they would do so with ozone, I think it would help.
Okay. Bruna Rodrigues asks, what are the characteristics of the ozone effluents when used on TCF comparing to the ECF bleaching?
Well, the main difference is that there is no AOX. That's obvious. Then there are some results showing that TCF effluent will have slightly less COD, but I personally have some doubts on that. I think basically the COD which is degraded which comes from the lignin is kind of similar. So somehow the bleach plant effluent is kind of similar with ECF or TCF. That's my feeling, excluding the AOX issue. But what matters with TCF is that bleaching effluent can be recirculated to the recovery boiler without any specific chloride removal step. So by choosing TCF, the effluent quality by itself is not improved, but the effluent flow can be drastically reduced. But because the bleaching effluent flow can be recirculated to the evaporators. And that's a big change.
Okay. Yes. What we see today here in Brazil is that many mills, they are having more strict legislation, or even lack of water in their mill sites, that they are almost obliged to decrease the consumption of water, and of course also to the generation of effluents, and therefore they are looking, of course, that these mills, and I'm not talking about just one, there are several, they are looking for ways to reduce water consumption and also to reduce wastewater or effluent generation. So in a simple question, actually it's not a simple question, but it's I would like just to have an idea. If you have a ordinary bleaching sequence, and then when you put ozone, what's the percentage of water use you could say we could decrease in this ozone sequence, more or less?
Yeah, I would say the water use, or the fresh water use, more precisely, can be maybe dropped by 40% in the bleach plant.
In the bleach plant, okay. Yeah, that's quite a lot, yeah. Okay.
Actually, the question of these effluent treatment plant issues is that people have a problem. Some pulp mills have a problem with COD, so they, after the biological treatment, they put a tertiary treatment. So most of the time, when we have a problem, we try to fix the problem. But sometimes I think it's interesting to look how we can eliminate the problem. And using ozone in the bleach plant is one way to eliminate the effluent tissue. Okay. And not to solve it by additional treatment means.
Mm-hmm. And is there any mill that is using ozone as a tertiary treatment to remove color?
Yes. No pulp mill, but paper mills. There are 4 paper mills in Europe using ozone as a tertiary treatment. 3 of them for hard COD removal, and 1 of them for color removal. But these are paper mills.
Okay. Okay, I think those were the questions. I did not receive any other questions here from our staff. So, Alexis, again, thank you very, very much for your great presentation. We learned a lot about ozone and the challenges, and I'm sure that ozone has a nice future in the pulp and paper industry, because all those aspects that you have presented, and because I'm in the environmental side of this area, I think ozone has a very large potential to be used in order to overcome these problems, especially related to water, wastewater, that the mills are facing, because it's a kind of industry that has a very large water consumption and generate also very large quantities of effluents. And so I think in the future, as you showed one sequence, a bleaching sequence, is a type of sequence that we need to avoid using as much water as possible, and also to generate less effluent. But anyways, again, thank you very much, Alexis, for your nice presentation.
Thank you very much, Professor Claudio, and thank you very much for the Universidad de Viçosa for the invitation. And if you have any question, any of you, please don't hesitate to contact me. Thank you very much. Have a good day.
Okay. Have a nice day.